Hey guys, this is a video over waves. It's going to be a quick review. I'm just going to go through some of the notes that we went over in class just to kind of review with you the basic properties of wave and Doppler effect. Okay, so waves, we know that they're the disturbance that moves through a medium. Anything that disturbs a medium. The medium could be air, water, a string in a guitar. So a disturbance that moves through that medium is called a wave. It carries energy but does not transport any matter. And you can see that you saw that through this linkies, right? So when you make a wave through this linky, the energy moves, but this linky doesn't go from your hand to the other person's hand. Okay. Now we said there was two types. We talked about transverse waves and longitudinal waves. Transverse waves are waves that where the oscillation and the wave propagation are perpendicular to each other. Okay. And we made a few of those examples of those with this linkies. And longitudinal are the ones where oscillation and wave propagation are parallel. Okay, these are sound waves. Sound waves are they are longitudinal waves. Okay. All right. We looked at the properties of a wave. We said that the wavelength of a wave is the distance between a crest and a crest, or a trough and a trough. The crest being the point that's highest above from the highest point on the wave, and the trough being the lowest point of the wave. And then we also talked about the period, which is the time required for one complete wave or a cycle to pass through a given point. Okay, and is measured in seconds. Remember that. Frequency is the number of waves that pass through a specific point, okay, every second. And the equations that we use were frequency equals number of waves, number of waves over time, which is 1 second. Remember that. And then period, we said that it was 1 over the frequency. Okay, so 1 over the period, and period equals 1 over frequency. That's how you can figure out. So if I give you the period, you should be able to find the frequency. Or if the frequency is given, you should be able to find the period. All right. When we talked about wavelength, then we used different diagrams to look at wavelengths and label those diagrams. Okay, but remember that they are related, wavelength and frequency. The speed of a wave, the frequency, I'm just labeling what the formula is. Well, we talked about how if the frequency goes up, since the frequency and the wavelength are inversely proportional to each other, okay, we talked about how if the frequency goes up, the wavelength goes down, and if the frequency goes down, the wavelength goes up. That also has to do with the pitch. Okay, frequency and pitch are related, so the higher the frequency, and I think you know this, the higher the frequency, the higher the pitch, the lower the frequency, the lower the pitch. Okay. Then we also talked about Doppler's effect, and the Doppler effect is just a change in frequency due to the motion of the source or whoever is listening to that sound. Okay, is the apparent change, and it's only affected by the speed of the source of the observer. So that's the only thing. It's not about the observer or the source speeding up or slowing down. It's about how fast they're actually going. Okay, and I'm going to put some drawings here. S represents the source, O represents the observer. We can think of the source as a fire truck with the sirens on, right? So the truck is coming towards the observer or the individual, and the siren is on. But as they coming towards the individual that's standing there, the frequency would go up, the pitch would go up, but the wavelength would decrease. Okay, and that's because this little fire truck here, right? The wavelengths in front of that are going to be closer than the wavelengths that are behind the truck because of the direction that is moving. Okay, they're moving this way, so these wavelengths are going to be closer or smaller, and the frequency will increase. Okay, so let's look at this other example. The source of the fire truck is moving away from you, if we think of the observer as you. So the frequency, right, would go down, the pitch would go down, and the wavelength would increase. Again, it's because that little truck is moving away from you. So if you're standing here, so the wavelengths in front of the truck are going to be closer, but the wavelengths behind it are actually going to be longer, depending on how fast that truck is actually going. Okay. All right. So the next one, the observer is moving, the source is standing there, but you're running towards that fire truck. So your pitch will go, the pitch that you hear, the frequency that you hear is higher, but the wavelength is shorter. Same thing if you're going away, the frequency would go down, the pitch would go down, and the wavelength would go down as well. So these are very basic examples of how the Doppler effect works, but just remember that it has to do only with the speed of the source or the observer. It has nothing to do with speeding up or slowing down. Because if I'm running towards the source and somebody else is running as well, but or I'm driving 100 miles an hour, but I'm slowing down, right? And they're 5 miles an hour and they're speeding up. That tells me nothing if I'm slowing down or speeding up. The thing that's going to affect the Doppler or the effect that I hear is how fast I'm going. I'm going 100 miles an hour. Yes, I'm going to slow down, but he's only going 5 and barely speeding up. So it has to do with the speed, not with the acceleration or deceleration of the source or the object or the observer. Okay. Now this is the equation that we use for the Doppler effect, right? The frequency that you hear equals the frequency of the source or the siren, whatever frequency the siren is given off. The speed of sound, which we know is 340 meters per second, unless it's specified, right? Plus the velocity of the observer over the velocity of sound minus the velocity or the speed of the source, okay? And we have an example here. Assume the source is moving away from the observer at 100 meters per second and has a frequency of 100 hertz. What frequency will the observer hear? So we know that it's moving away, so just by looking at this right here, we know that the frequency will go down, the pitch will go down, and the wavelength will increase, right? Just by knowing that the source is moving away from this stationary individual or this individual that's not moving, right? So we can fill out your information in our formula. The frequency that we'll hear equals is 100 hertz, which is given, times 240, the speed of sound, right? Plus 0, because the person is not moving, okay? Or the observer is not moving, over 340 again, because it's the speed of sound, minus 100. Because when you're moving away, the speed that you're going to use for your velocity or the velocity that you use will be negative. So this is another note. So for this one and this one, when you're going away, okay, then you're going to use the negative velocity, okay? Whatever number they give you for the velocity, you're going to use the negative. When you're going towards, okay, then you're going to use the positive number of that velocity. So that's what we did here. So it would be frequency equals 100 times 340 plus 0 over 340 minus negative 100. Well, if you do the math, you come up with 77 hertz, right? But what if you flip the direction of the source? What if instead of the source going away from you, it's coming towards you? Try doing the math real quick, and then I'll show you the answer in like a couple of seconds. Or pause the video, do the math, and see if you get it right. So this is what you should have, 142 hertz. I think it comes out to like 141 point something, but it rounds up to 142 hertz if the truck is coming towards you. Okay, so that's Doppler effect. That's the introduction of waves. Use all your notes, and we'll see you for the test.